No. So, okay, we'll start some fire up here. We got people sneaking in. There's so arrows don't like to use stupid machine. Does this help you? No, I don't know if it helps or not. I don't know. We'll see if this works. So again, in previous talks, I used to have these funky diagrams to show how the compilers put together on Alpha and Titanium, and all arrows and boxes, how we replaced GEM with LLVM. I don't show those anymore. Trust me, you go back and find them in old talks if you want to see how the boxes are put together. But we essentially replaced the GEM back of all the compilers with LLVM to generate code for x86. That's the simple part. People, there's the bright screen to blind you. If you want to know the current, we updated all the compilers new just in the past month. So if you haven't been to the support portal, you'll find new versions of every compiler out there. Highlights I want to point out. I finally, Pascal, the last compiler ever to switch over to PCSI, I finally did that. So that's the last one of the bunch. Nothing is really, so most of them is small bug fixes and debug support. We'll talk about debug support in a minute. Most of the focus for all of these things have been getting debug support back to the Titanium level, and I wasn't ever happy with that. Maybe even a little better than Titanium. So the debugger itself, so the besides getting the compilers hooked with LLVM, with the new code generator comes a new, better form of the dwarf intermediate debug information. And our debugger on Titanium was so addicted or dependent on what GEM backend generates for dwarf. So dwarf is supposed to be this arbitrary thing that every debugger should be able to swallow all of dwarf and do the right thing all the time. And the answer is, our debugger was just insistent that it does it in the same way that GEM did it. If not, it was just not going to work. And we had to tell the debugger, calm down. You get to see different dwarf from different backends. You need to go learn it. So we've actually had to rototill good chunks of the debugger just to make it be tolerant of dwarf that it, in my opinion, should have been tolerant of for the past 15 years. But that's what's been going on. The debugger in 923 update 2, update new, and update 3 is a better debugger. But in many cases, the compilers and LLVM had to be taught about some of the legacy VMS dwarf tags that LLVM never heard of. So we had to teach both halves, the debugger and the compiler. So between the better compilers that are available now and the better debugger that's in update 2, if you haven't updated to update 2, do that. And then when update 3 comes out, that's also, we're just constantly making bug fixes to the debugger. So if that's important to you, please do that. Now, there was only a few of us in Bob Gazelter's talk this morning worrying about why would you use the VMS debugger? I can tell you, I use it all the time. It's a good user mode debugger. I know Doug doesn't. If you're in elevated mode, you can't really use the traditional VMS debugger to debug an execlet or a device driver. Paul would never want to use the VMS debugger. You just can't, right? But I like the debugger. I debug the compilers with the debugger all the time. Yes? Eh? So there's that. That's just the debug. That's what, so, you know, people think that the debugger is the same on every platform. It had to, obviously had to learn about all the new hardware registers and everything else. The debugger is much more hardware sensitive than even you would expect the debugger would be. We're talking about macro again. When I looked at all the compilers, if you're used to the Titanium versions coming to x86, Fortran is Fortran, COBOL is COBOL, BASIC is BASIC, the same front end, literally the same front end. We just recompile and go. So if you can force a program through the Fortran compiler in Titanium, it should go through the Fortran compiler in x86. If it doesn't, tell me. Macro was the harder one, right? So macro, on Itanium knows that Itanium had a lot of registers. So all of those alpha registers you know and love, R0 to R31, were put into Itanium registers, and we fit them all. So a macro 32 moval or an addle was really a register to register to register operation on alpha and on Itanium. Get to x86, there's not enough registers on this system. Physically, there's only 16 registers. It feels more like a VAX, but it's even less than that. So all of the alpha registers in a macro 32 program are memory locations. So there's memory locations, these pseudo registers, they're treated just like machine state. Interrupt happens, we save them, we put them back. ASTs happen, they get managed that way. Multi-thread, they get managed that way. So the entry point, if you look at the generated code from any macro compilation, the prologue of every routine calls a system routine that says, give me the address of where my registers are. And then for the course of that routine, I have to fetch them, operate on them, put them back. So the addl3 right here is 2 memory fetches, an addition, and a memory store, whether you like it or not. So in the past, if you were writing in macro to be really efficient, Brian, you get here on this platform, it's like, really? You know, and right now it's pretty dumb. You turn around and use R4 in the next instruction, you're going to watch me fetch it back again. And Brian's going to say, you just had it. Why did you bring it back? And the answer is, yeah, it's a relatively, load store model. We try to do some things, but it's a harder thing to do, right? So anybody who wrote macro thinking it's the highest performance thing on the planet, rewrite it. It works just fine. Obviously, the operating system is still the big chunks of macro, and it works just fine. But if you look at the generated code, you get people pointing out and saying, this is really inefficient. We have plans on making it a little more efficient, but there's things I just can't skip. So, macro. But you can compile it, should work just fine. Just don't look at the code. And there's tricks too. I mean, every VAX program on the planet, you put the return address, you put your return value in R0. But if you're a macro routine that was called by a C routine, C doesn't know about these funky magic registers I've got off to the side. So I've got to put it in 2 places. And when you get called, I got to get them from 2 places. It's uncomfortable. That's the best we can do. So. So how many, other than VSI people, are there people who actually do macro coding besides Brian? Actually, some. I mean, not much anymore. There are some people I know. I was talking to Colleen. There's some still pieces in RDB that are written in macro. They're trying to rewrite. Internally, the running joke is any module in the operating system written in macro, you convert it to any other language, I'll give you $5. And I've paid out. Like a slot machine. If you give me, and I've given, now of course you can't just write one to check it in and rewrite it, and you can't game the system, but I've let people do that. And anything is better. I just rewriting it from macro to COBOL, you might get better. So for the legacy compilers, same things. Again, I tell people, well-written programs port with no modifications, and none of you here have well-written programs. Every program has bugs in it, whether you like it or not, and I don't care how many AIs you feed it through, there are going to be a bug in it somewhere, though the AI probably will replace one bug with another bug. Good notification. So it works fine. Things that we have found, for the few people that were at Vadim's talk earlier today, the type of things you see, every port I've ever been involved with will shake out these broken programs. And you'll find them. What we've seen here is on Alpha and Itanium, our back end, we always left some alignment holes because early alpha machines in particular liked things on aligned boundaries, and they like to do things in quad word chunks. And if you try to do things smaller than that, it always turned into more code and slower code. So GEM added these alignment holes everywhere. When we went to Itanium, we left the alignment holes. It helped a little on Itanium as well. We just left them all in there, but it really made it easy for you to have a program that did a 64-bit store on top of a 32-bit variable. And on these other systems, all you did was clobber some alignment holes that no one was using, and you essentially got a 64-bit variable. If you kind of get free promotion. LLVM doesn't. No, on x86, alignment doesn't matter. Well, if it does, it doesn't matter to us. It's hidden down into the micro engines of all those chips, and that 64-bit store to the 32-bit variable almost certainly writes somebody adjacent to you that's important to you.
I was working with a third-party program, working on one customer system.
Yes.
WASD, and I brought it over to my system to try and use it, and it didn't work.
Mm-hmm.
And all I can think, because of a variable too small,
mm-hmm.
all I can think of is somewhere down there in the hypervisor, microarchitecture, change in write order.
Maybe. So write ordering on x86 feels a lot more like VAX did in terms of reads and writes. All the memory barrier stuff you always had to do on Alpha if you had multiple threads writing the same locations. x86 kind of their default behavior is the same-ish. So but I haven't seen many of that before. That hasn't been something that we've noticed. But maybe.
It can be there.
Okay. So we had that as well. So we've had a lot of stuff. That was probably the one that has shown up more often. So again, you've heard us talk a little bit about future native builds. We've compiled huge chunks of the operating system with native compilers, which means images are smaller, less code, less filling, tastes great. But now the optimizer gets in. I know there's people, including on any, have asked me here or even online, again, does this LLVM optimizer, is it going to expose any bugs in my code? And that's just, yes, I said there are bugs in your code, and you should thank us for helping you find it, but the way you find it might be a little, it's not like I point them out to you. Now, I said, if it's easy, you would have found them all by now. The other one we've seen a lot is the uninitialized variable. So the gem optimizer, sometimes we would see a code path. You only initialize a variable in the then part, not the else part, and all the subsequent fetches we've said, well, yeah, it's either initialized because you went through the then part, or is random, you went through the else part. But we left that in there because it didn't really make it any faster for us to substitute it out. But LLVM seems to really love to do that. It says if there's any code path where the variable then becomes uninitialized, it's like, this is an invalid program. And guess what I get to do with invalid programs? Anything I want. And so it says the way to make this broken program faster, is they replaced every fetch with just here's a literal 0. Because if it's uninitialized, why bother going to memory? 0 is just one of the many values you could have gotten from that, which means the times when you went to the then part that gave you a good piece of data, which might be 99% of the time, this program just gives you zeros all the time, right? So we had some internal tools where in C, you can have the C front end pre-initialize all your stack variables with a known bit pattern. Mm-hmm. We have an internal switch where we can do that with Bliss, Pascal, COBOL. It just pre-initializes everything, just so LLVM says, fine, I know it's at least initialized in every path. And then we would do that and say, oh, the program's working now. And then that gives us a clue internally. We should go look for uninitialized code paths. Now, the C compiler or other compilers in the past will often tell you about uninitialized paths, but with data flow or other stuff, it's sometimes hard to find the uninitialized variables. And that's actually one of the differences here. The GEM backend would help us find them, and we report them back to you. LLVM, I I don't know if I haven't found a callback yet in LLVM optimizer because it says, here's initialize. I'm going to remove this fetch. I would like it to tell me so I can tell you and say, hey, we removed this fetch because we think it's a 0 all the time. And you, the human, can say, no, it's not. It should be something valid. And then maybe you'd figure out with you, where you're going wrong. But those are probably those are the two that we've seen the most. And I
generate warning.
I want to generate a warning, and I've yet to find a way for it to tell me that. I mean, this is Linux world. I mean, there's these Clang and everything else as a Linux reference compiler. You're supposed to be smart. Like I said, you can insert your own joke there, but it's So, but for us, and when I see these are the most common ones, I don't know if the Vadim gave numbers this morning. I mean, when we just, and I'm not talking like we see these things in hundreds and hundreds of instances. I mean, this can't be more than 20 times that I've seen these type of failures. So it doesn't happen a lot, but these are the ones that we've seen more of. Bob's coming up with the crank candy.
No.
He's double-fisted drinker. He's got a to-go cup and a regular cup.
Yes.
Okay. So
Just hit the refueling anchor.
So that's all this for the legacy compilers. Again, Pascal's Pascal, Fortran's Fortran. C++. This is the one that's always been the hardest one on every single platform, whether it's Alpha C++, Titanium C++. C++ seems to be different for reasons that even I don't understand. They seem to just be a little more, in my mind, I'd much rather have done it. I should put this on the microphone. An Ada compiler probably would have been simpler than trying to drag a C++ compiler on, except more people ask for C++ than Ada. So again, a little background here. The C++ compiler is not the same one for Titanium. No, not a shared source line at all. The Titanium C++ compiler is using a front end based from a company in New Jersey, EDG, hooked to an Intel backend for Titanium. On x86, it's the LLVM Clang front end, so industry standard Clang front end hooked to the same LLVM that Fortran and C and Basic and COBOL hooked to. So exactly the same back end. We all link against the same OLVs, but the front end is industry standard Clang, so it accepts every stinking language feature that you can type on a Linux box, including some that I really wish you wouldn't. There's some we don't support, and we provided it with two command lines. There's a DCL command line, looks just like the command line you have in Titanium for C++. So if you have command files, make files, it should just work. But we also give it to you in a form to give you a foreign command. And if you want to have a Linux style command line, you can type the Clang command just like you would type it on a Linux box. And the last time I checked, Clang itself has like 500 command line options. There's a lot of them there. I'm going to promise you, none of them were ever tested in combination with each other. A lot of them are strange anyway, or some are not for x86 targets, but you can use them all. You can go Google Clang. You can find all its command references at llvm.org. You can find them, and you're going to try some strange exotic command option, and you're going to hurt yourself, and you'll complain to us, and I'll say, that's just, you had a boo-boo, here's a Band-Aid, but I'm not really going to work on why, the 800 option.
The make script will work. That's
at
least theoretically.
It'll compile. You may find it won't link, or if it links, it may not run. So there's a handful of those, but that's kind of the background on C++. If you haven't been following along when we started the version, when we first got it, of course, it had no listing files. Who uses listing files on Linux? They don't exist. It's a concept that they don't want to talk about. Who would ever want to have a record of what the compiler saw?
But now we have
We do. We've added listing files. So we went and we added so many things to the Clang front end to make it VMS happy. We added dual size pointer support. We've added Listing files. I will warn you now, and I think I don't have this in the next slide. Did I? Oh, yeah, I did. So the difference in titanium, for years, people said, John, your C or C++ on titanium, the size of size T, or you size subtract. On titanium, the thing that burns people all the time, you have two 64-bit pointers and you subtract them. That's a 32-bit subtraction. That's just the way the language is, because in the C or C++ language, two pointers can only point into the same variable, not into two different places. And if the biggest variable can only be 2 to the 32 big, then the distance between those two pointers can only be 2 to the 32 big. And so the subtraction of two 64-bit pointers was always a 32-bit subtraction on alpha and titanium. And everybody, including me, says, that's the stupidest thing I've ever seen before. It makes no sense. But if you think about the anal retentive language standard description, it's like, yeah, fine. But in common practice, it's not what people expect, right? So here for x86, I said, look, you want an industry standard C++ compiler, you better get used to industry standard C++. So when we first got it out of the box for Clang, it had only 64-bit pointers. That worked for about a week until somebody says, ooh, descriptors. Then, we add the dual size pointers. You had to add the pragmas to manage those dual size pointers. You got to have the qualifiers to manage them. We work through, but the ones that we have stuck with, for better or for worse, long is just like Linux. You go to a Linux box and a long is a 64-bit thing. Long on alpha, long on titanium is 32 bits. And that was a legacy thing from VAX to make things go forward. And longs were left to be 32 bits because we were afraid that people had a header file that used a long on alpha on VAX and is a 32-bit thing. We left them 32-bit separate. Again, this whole trying to be friendly, upward compatible, recompile and go from VAX to anything was a great thing, but it still haunts us today.
Problem is that if you're passing data structures around, you can have real problems.
Yes, you can. And so, yeah, and we did. Again, you get names, and with compilers traditionally have always upcase names, but not on Linux. You have it, you type printf and you get lowercase printf. You go to a C program on Linux and type printf camel case with the big P up front. You're not going to find a routine called big P printf, right? We've left that
Actually,
in
it's
there.
not true on VMS. You have to, unless you have to unless you enable the program.
Every compiler on VMS up to this point uppercases external names. Every compiler, unless you ask for names, it possesses.
Even C++?
Every compiler by default on VMS up till now upcased external names unless you ask for anything else. We flipped the default.
Okay.
The default is here for C++. We leave them alone unless you ask me to upcase them. The idea was going forward, you want to be part of the new open source environment. We're going to give it to you. And if you want to go back and say, run back and hang on mom's apron strings and say, I want what it used to be, you can get them all back. Again, you can have names. The linker doesn't care how long your routine name is. You can have a routine name that's 8,000 characters long. One, you'll never type it, and you'll never find another language on VMS that'll have 8,000 characters. But we just left that all in there. Why bother? So we a couple things we didn't do. There's no VAX loading support in the compiler. We didn't think anybody used VAX. It was in the Titanium C++ compiler because that backend was taught to do that. We haven't. I'm not going to go to the LLVM community and teach them about a floating point format from VAX. So that's kind of where. So for the most part, again, well-written C++. Insert joke here. It does okay. We have used our Clang compiler on VMS to build Clang on VMS. I mean, we've built itself natively, so it can process all of that. And because the Clang and LLVM source code is well defined to use only a subset of C++ features, fortunately, the subset that we've implemented It doesn't use all the weird features. Okay. So there's C++. If you have C++ code, it usually now works fine. But just remember the big one still bites people is the long, and then that propagates through to this other things like size t. You can have two 64-bit pointers and subtract them. It's now a 64-bit subtraction. It actually doesn't hurt your brain anymore. It's like two 64-bit things, subtract them, it's a 64-bit subtraction. So here's that one. I think that's enough for C++. Futures, what we've done is one of the things that you'll notice today on 923, you'll say, I've got a C program, I want to use a long double. I've got a Fortran program, I want to use real star 16. I've got a Pascal program, I want to use the quadruple. None of that works because the older LLVM that we use to build the operating system today doesn't know about 128-bit extended floating point. It was about 80-bit extended floating point, and that's all it knows. Newer LLVMs know about the other floating points. So the idea was it won't work until I get you a language RTL, math RTL, libRTL that was built with a compiler that knows about long double, which means native compilers, native builds. So if you've had any long double up until now, you'll find that it doesn't really work. The release notes tell you that it doesn't really work. I have not been, the castle has not been stormed. I have not received any nasty emails about long double.
Mm-hmm.
So either no one has noticed, no one cares, no one's using it. I don't know. Some of the compilers like C and C++, you can tell the compiler to treat long double as a double. But some of the compilers, you can't do that to Fortran, you can't do that to Pascal, you can't do that to BASIC. So I just want to assume no one's using it. Or you haven't ported x86 or you haven't noticed. So it's working on the native build things we've done internally. I can bring up a native build system on my laptop now, and guess what? Long doubles all work. You can do a long double cosine. Let's see. We're working on the debugger. People notice machine code listing still isn't there the way historically GEM generated the machine code listing. So it had symbolic names, it had interesting line number information, and it had both the code and static data. It was very useful if you're trying to debug at an instruction level. You don't get that in the Clang LLVM world. You get just the object file that comes out. So analyze object kind of dumps out the code. We give you line numbers, but you get very little symbolization. You don't see much about the static data. We want to do more. And again, I am hesitant about going back to the LLVM community and saying I want to just rototill your back-end code generator, because remember, it's a multi-target code generator. It's even harder to stick a 4-foot screwdriver into the LLVM back-end and make massive changes there.
What about its
Well, again, their disassembler, there is an LLVM disassembler, but it really feels like object dump. You just get code. It's really hard to, static data doesn't disassemble very well with your disassembler. An analyzed object just doesn't disassemble static data very well. That's why I have to fix this, right? You don't see static data in the analyzed object just on x86, like you would on an alpha/list/machine code or a Titanium machine. But that's why it's on the futures list. I want to fix that. I think that's it's nasty to do that because the analyzed object disassembler doesn't have enough semantic information to know the names or the data types. I have a bunch of bytes in a PSEC. Was that a string? Was that a record? Was that an array? What was the shape of that? It doesn't know. It could analyze object just up to this point, has not read much about dwarf, and it requires you to remember to compile as dwarf. You want the compiler to always give you some minimal dwarf, whether you asked for it or not, and then do you want me to make the object files, linkers, and the executables bigger? On the outside chance, you might want to get a dis of files. All good questions. Refresh LLVM, even the native, so the cross compilers are built with a very old LLVM. the native compilers, all the ones you can download today, are built with LLVM 10. They're up to 21. Now,
the jump.
the LLVM community increments their major numbers a lot. They like to bump the numbers up. It's not like VMS where you bump up numbers and meaning it's not compatible with older stuff. It's more, I don't know why, to be honest. It's almost like the 21 is like, that's almost like a quarterly release. And then the 1.3, they do updates on top of each quarter release, and they have short-term threads, longer-term threads. All I know is we're now trying to, when we started this whole porting, we grabbed version 10 and then figured out where all the missing VMS pieces were. We now have all that. And so all we're doing now is to pick up this one and we're merging them over. And it's all in Git, it's all in Bitbucket, for better or for worse. And Git does a pretty good job for merging that over. And at this point, we're still in process of it, but I'd have to say 80% of the things we did to add VMSs into LLVM 10, that code is pretty much still intact in LLVM 21. So the merge just happens. We found a few where we go to merge the code over, and guess what? Somebody in the LLVM community has rototilt that code, and what used to be one file, one set of modules has turned into 3 files and 40 sets of modules, and we just have to re-implement that and remove it around. But at least we know what we're doing this time. Insert joke here. We may have never known what we're doing. But they've done that. For the most part, it's not been difficult. We haven't come across anything of like they totally removed something. It's just been they've moved things around, for better or for worse. LLVM 21, again, like everything else, better optimized or better this. They've added better security features to it. I don't know. There's a long list of changes, many of which are probably not relevant to the VMS community. But again, I want to keep up with the current Clang, because the newer Clang that goes with this has like C++ 22 compiler support, all of the stuff you can get in newer versions of C++. Again, whether using them or not is a smart thing, I don't know, but I want to, I want to get out of the days where people used to pick at VMS and saying your compiler is out of date. I'm not going to go to your platform. I can't bring any random piece of open source over to VMS because your compilers won't handle it, right? So I want to do that. It means, of course, I have to make the headers and the RTLs do the right thing too.
Yeah, and that means you have to provide more header files.
Yes, we do have a list of more header files. Some of the stuff, it bubbles into not just headers, missing CRTL interfaces, missing pthreads interfaces. And anytime those happen, especially in the missing pthreads interfaces, does that bubble into missing debug support, missing linker support? You thaw, yes.
In that list is standard atomic in there?
You would want it to think so, because that comes out of C11, and C17 has that as well. We talked about using C++, but Clang is also a multiple input compiler. Clang is both a C compiler and a C++ compiler and an objective C compiler, if you care about that. And so you can feed C code into Clang and it'll say, oh, C files, I'll become a C compiler. And it does all the things a C compiler should do, which means, yes, standard atomic, any of those single threads.
URCU, user mode read copy update.
So there's a long list of things that now that the compiler could, dynamic routine binding. There's this thing called iThunk that you can do on GNU on Linux boxes. So you can have like a thing of memcopy, and you can ask Linux box, I'm using memcopy, but at image activation time, call this routine, and it'll tell you which memcopy you should use today. Are you on an AMD machine? Are you on an Intel machine? Are you on are you on a better Intel machine or an older Intel machine? Maybe they have different performance models. So you essentially get this runtime binding. And the answer I'm here to tell you is no. So there's things like that we will just stub off. You get the mem copy that you got out of the CRTL. And if you don't like that, well,
Well, but some of that, what you just said, has to go to different processors have different rewrite optimizations.
Yep.
And when you're trying to the user mode recopy update, which is per threaded programs, it really matters.
so newer function. That's one of the reasons historically they didn't want to go to a newer version of language standards because it means you have to think about these things. But yes. So that's a little bit of work here. Again, there's some stuff in LLVM, there's some stack smashing stuff in the newer LLVM. So in theory, when you do a return in the epilogue, it'll make sure that the return address on the stack is still the same return address. It's like the Intel Shadow stack that they have in some of the hardware, but there's some instant stuff in there. We still want to talk about thread local storage. We didn't talk about when you do threading, you want to have thread local storage, which means historically, it's the image activator that brings your code in from the disk and creates the static memory that all your static data goes in. Thread local storage means every time a thread gets created, it needs to have a chunk of memory allocated somewhere, most likely on the heap. But and then there is additional relocations that the linker has to process, and the image actor has to process, the debugger has to process, SDA has to process. The librarian has to process, perhaps. So there's a long list. One small feature.
Destructors and constructors too.
So we have most of those today. I mean, so historically we have libdar initialize that you all know and love. Starting with C++, the unit operator.
It's a native part of C++, right?
But we have, yes, but we support their .ini arrays and their .thimi arrays. So we actually do that. So we actually. It's probably not written down somewhere, but there's actually two competing initialization functionality that goes on in there.
That's the nice thing about it. Like X. There's a possibility of everything.
That's right. So that's and then LLVM has a lot more, again, language sanitizers to look at code that look for free after use and stuff like that. It's really very C++ centric. I don't ever imagine being able to run some weird LLVM sanitizer on Bliss code. Or even worse, macro code. I mean, if you're worried about free after use bugs in macro code, you really are on your own. And the challenge with macro code, I tell people is, we have do I have any of my management here? No, good. So hopefully they won't listen to this either. I mean, a lot of them, it's like, well, can't we use an AI to convert our macro to some more modern language? And my comment on macro is most good macro code was written a long time ago by smart people, and it's not just an algorithm written in macro, it's an optimized algorithm written in macro. They manually hoisted something out of a loop and put something into a register, and they've done these weird linkages between routines because I'm going to leave this in R5 because it's going to be used elsewhere, and it'll come back in R5. That wasn't part of the algorithm, that was part of the clever implementation. So your job, or an AI's job, is to take that random piece of macro and extract the algorithm. Tell me what the algorithm is. I want to rewrite that into a modern language, C, C++, Rust, whatever, and then let a modern optimizer shuffle it around. You don't need to replicate and have a local, variable called R5 and have the C code fill in R5. And to be honest, any program I've ever tried to do language conversion, you end up with a C program that has a variable called R5 in it.
Actually, the problem is
not maintainable.
Well, that's the problem. The problem is you can brute force macro expand, and a good code optimizer will optimize it decently
and unoptimize it for you.
But it'll just straighten out all the
maybe.
The problem is, if there's a bug, finding it
correct
is a cast iron bleepity bleep.
You have again, we don't have a lot of macro people here. I'm probably spend too much time talking about macro, but you have these older legacy programs, and we really want to know is make them portable to newer people, modern people who don't want to learn macro, don't need to learn Bliss. And the answer is, I want to extract the algorithm into some modern language, and then you can work on the algorithm. You can work on that source. You don't need to look at a piece of C code, and what you're seeing is C code with the echoes of macro past. So that's features.
Macro compiler will do very nicely to porting to a limit, but when you're trying, but extracting the algorithms are a mess.
So of all this thing, we had calling conventions. Again, sticking with LLVM and with Clang, we picked the Linux ABI calling standard. You can take a .o file, go use Clang on Linux today, or even GCC on Linux today, because they're all the same. Take that .o file, bring it back to VMS. Our linker will take it. You can take an obj file from VMS. I'd say on C, do prefix equals none, so printf stays as printf. Take that obj file, take it to a Linux box. You have a good chance of linking it. Now, of course, it's full of VMS-isms. You're going to go there and it's going to say, what is systar_qio? What is lib$ this? So you probably won't get very far linking it, but we've left, unlike on Itanium, where those ELF object files were really, our linker was not tolerant about anything that didn't start and end on VMS. The linker now, we've done this. We can move these objects back and forth. I don't document that. I don't encourage it, but you can. If you go, you can take those object files back and forth and run them with the Linux. Take a VMS OBJ file, take it to a Linux machine, and use obj on it to work just fine. So we're trying to be more in line with open source compatible stuff. Again, my challenge is to make VMS look like Unix without making VMS look like Unix. So we did that. Like I said, we picked that. We did add a few things we have to do. Everything needs an ARG count. There are so many interfaces in VMS that would not live without an ARG count. Again, my time machine's broken. If I had a time machine, I'd go back and ARG count might be 30th or 40th on the list of things I might want to take care of. But we have that. So we've done a handful of things. Remember I talked about those weird alpha pseudo registers? We had to extend the standard ELF extension handling stuff. So when you unwind, I got to put those alpha pseudo registers back. That's all in there, finally, right? Rob and I struggled. We found a place where we missed a place. And with FMS, FMS worked just great, except if you let it sit on a particular screen and let a timeout happen, FMS wanted to do an unwind, say, okay, no one answered. I'm going to get out of here and go back. And one weird path, and the Bliss code is using registers and weird linkages, and we forgot to put a register back, and somebody got upset, right? So there's a whole bunch of stuff in here. But the big thing I'll talk about here is this memory model thing. And that's kind of what I'm going to talk more about. So on the Linux, when you compile things, go and do a CC, hello world.c, they assume what they consider a small memory model, that the code and data, everything can be jammed together into a 2 GB section. And everything's just done that. And if you do a jump from one routine to the next, all those text sections are all near each other, and everybody's a one big, happy, small family. Except on VMS, we're not doing that, right? We've put code in 64-bit space to get it out of 32-bit space by moving, we've left 32-bit space because you want your heap. Remember those descriptors that have 32-bit pointers in them? So if you have static data, things on the stack, we tried early on, Drew in particular back there said, John, when we started the port, can we move the stack to 64-bit space? Wouldn't that be lovely? Because every Linux box on the system in the world has a stack with a 64-bit address space. And the answer is, have you seen descriptors or item lists? Have you seen this? And by the time you do it, it's like, I can't avoid those interfaces. And I'm not going to tell you to recode every program that used item lists or descriptors. Have you seen macro code that does a push hold to get an address or something on the stack? So the answer is we were stuck with this mixture of, I got to keep some things in 32-bit address space, but I want to get all that code out of there so you have more room for heap, more room for stuff. So it was that was the benefit of moving that code out of 32-bit space, is to put in 64-bit space. But now I have code way up here. I have data way down here. That's bigger than 2 to the 32 difference, 2 to the gigabyte. I mean, if you look at the address space subtraction, it's a huge difference. So in the calling standard from AMD, they have then these medium and large models, which kind of support much larger code in a more sparse address layer. Some of them, the large one at, a little extra code, we didn't want to do that, but the medium one kind of felt, it's like mama bear, papa bear, baby bear. We picked the medium porch, and kind of stuck with that. It's still not quite the same fit. The big thing on VMS that Linux doesn't really have is, so if you take a normal Linux GCC, all the code gets put into this one section, psect called .text. You can tell those compilers, can you put each routine into its own psect.text, routine name, .text, routine name, but the assumption still they all get globbed together. You link it together. On VMS, we have things as a system where you've got a module, you can, especially in macro, you can chain psects, and I have some routines that you want to stay in 32-bit space in this psect. I have some routines that want to go to different psect in 64-bit space. So I may have routine A, call routine B, one of the routines is in 64-bit space, 2-bit space. Then just no user program really does this. The operating system does it. So we had to do all this shenanigans because I have this kind of code scattered around the system. I wasn't willing to ask people to rewrite huge chunks of the operating system.
We wouldn't have listened even if you
asked. So here's a place where I've told you, about 5 years ago, I had a quick talk at LLVM. You go to the LLVM web channel and just search for my name. I've got 2 talks in there. I gave like 5 or 10-minute talks in the past. I'm probably going to do something. So I leave here next week to go to the LLVM conference in San Jose, but the next one in the spring, we're going to submit some abstracts. We're going to give some talks. I want to tell them now that we're done with all this, I want to tell the rest of the community, this is what we've done. We have not merged any of our code back into the LLVM master repository yet. The LLVM backend changes, I think there's going to be no problem there. They've been relatively small, all of the changes. The Clang front end changes have been a little larger. I don't think they are going to want me to throw listing file support into their repository. That might have to stay out of tree for a long time. But so we kind of did all this. So we picked it, we stuck with the medium one, we've made some changes. You can go download the ABI if you want. That will put you to sleep. None of this, if you want some light reading at bedtime, read the calling standard, or our calling standard in our docs here. I think this is a more well-written document. Same stuff that covers the VAX, alpha, titanium, and x86. Read that one if you must. Right, I kind of hit some of these before. The other one is that every time we've done a port, the linker is usually the bearer of bad news. It has to do more work every single time. VAX linker is really boring. Alpha linker, not so boring. It did a few, sometimes transformations to your program. Itanium linker had to make some little PLT routines of bouncing from one place to another. The Itanium call instruction was a start from here, go this many bundles this way, or that many bundles back that way. And what happens if you can't reach that far? It's like a 21-bit bundle address or something like that. So the linker had to make little baby trampoline routines on Itanium. You don't see them, but they're there. x86, even worse. You might talked about you have descriptors that have 32-bit pointers. If you think about it, there are several places in the VMS operating system where people expect routines to have to be addressable with a 32-bit pointer. Declare exit handler. There's a handful of these. We have declare exit handler 64-bit legacy code, declare exit handler. You may have a particular piece of, again, back to macro code, you have a move AB of moving the address of systar QAO into register 5, and then later on you want to call through register 5. Register 5 is only a 32-bit register. How do you reconcile the fact that I just got through telling you I've moved all the code to 64-bit space? What happens? How do I access the 32-bit pointer? And there's no data structure. On x86, the address of routine is the address of the first byte of the instructions, just like VAX. right? There's no procedure descriptors, no calling, no unwind, no function descriptors like we have on Alpha and Titanium. How do you do it? Well, guess what? The linker makes trampolines. And we're going to see in a minute, you link a program, whether you like it or not, every routine you have has a little companion 32-bit trampoline routine that will bounce to the real routine. And if anybody ever needs the address of a routine, you get the address is 32-bit trampoline routine. So I said a minute ago, all codes in 64-bit space. I've lied. All codes in 64-bit space except the stuff we put in 32-bit space.
You mean except for the Miley Cyrus song? It was good until it wasn't.
Yes. So there we go. So that's kind of that. I'm going to show you. So here's a quick one. I've got a small Pascal example here. And if you haven't looked at a link map in a while, congratulations. If you have to look at a link map, you can kind of see things where the linker kind of puts things into these. These are here for clusters, but I want to put an executable here. We'll go through here the next slide. Same. This is what you would see in the link map here. That this is the static data strings built with those type of static strings. Everything stays in 32-bit space. I'll need the address because you might make a descriptor. The code for that little routine, all going to be jammed up in P2 space. There's this thing called, you don't really call it exception handling data, or you'll sometimes hear us calling it the GOT, the global offset table. The code is relocatable. It's code. So there's no address constants in the code, but if you need an address constant, where does it go? Like on Alpha and Titanium, there's the short sections and stuff with address constants. The linker had to put them all somewhere. And on x86, the way that an instruction needs to go, you have just relative offsets. The instructions on x86, you want to load something, it's load. There's a called from my current PC, that far forward or that far back. So if I this
base,
it's a base register. So it's RIP addressing. So RFU, the instruction pointer. So if you're looking for something, depending where you're at, it's this distance, but you would execute a few more sections later, distance is farther. So the linker has to keep computing arithmetic, but it's arithmetic's easy for the linker. It just does a lot of it. Right? So you see these things, and as you look through, the code's there. This is at some fixed offset because the instructions in here, I need to know where they're at. If you move this stuff around, even in a shareable image, it may not load these addresses, but they have to stay relatively with a relative same position between them. Again, this is the GOT. Again, if you went there in memory, you would see a bunch of 64-bit things. And this is where the image activator probably would have to fill them in. We'll see in a minute. There's some things the linker can fill in, but the linker doesn't know where the address of math $square root's going to be because it's get loaded in some other address, somewhere else. You see then back in P2 space, P0 space, bunch of trampolines. If we looked in there, we'll see they're all just trampoline. They're just one instruction long.
Before you leave that slide, I'd like to ask a question to the group. Anyone here using ACMS? Okay, good.
Good. Thank you. Right answer. Back here again, more stuff in the link map you want to see. This is the same vision of those segment things, but now just more at the module P sector level. You can see here the read-only data from the one module Hello World at address 200. It's 42 bytes long, yada, yada. So all these things, it's the same set of numbers we saw in the last one. And you can see, though, my cut and paste, this is a duplicate. This isn't listed twice in the real link map. I just cut and pasted for it. But you can see the linker. I don't know. It's true. It's other trampoline routines, but they're I don't remember the name of how it got $0. But let's skip that. But you kind of see now owned by who recreated these sections. There's linker code, trampolines, linker other PLT routines. There's linker generated exception handling data. there's linker generated. This is a table to the exception handling data. It's like a binary table for the people to find them all. And then this address, there's all these generated addresses. So when you look at the size of the final program, your code is a small piece of this. So again, when people were doing this native stuff with VMS and compiling it, like, isn't the thing going to get smaller with an optimizer? Won't these images get really small? Yeah, I can probably turn this 42. I mean, this 83. What if I turn this 83 into 3? 80 bytes out of this whole thing, just, it doesn't make much difference. It's noise. So, so that's why it's hard when we do a comparison of cross-built systems, native-built systems. You're going to say, why is I do a dir slash, size? Why is it not much smaller? It probably is, and it might be much faster, but you can't tell from the exec file, right? You have a hard time telling from the map, right? Again, stepping through here, you can see the code. So that was, one segment, another segment. Here's the multiple code that got collected into the executable segment. We have the exception handling segment and the DOM. So all the stuff is in here. Right? If you looked at the analyze object distance, so the object file, the distance between our current PC, and so this is a got PC rail relocation, says, dear linker, I need the address of that thing. I don't know where it's at. And I need that address to be put in the GOT table. And what I want is the distance from here to that slot in the GOT table that will hold the address of that. So the linker says, great, I know where the GOT's going to be. It's fixed offset. So I know what that distance is, but I really don't know what that thing, where it will really be. The GOT table will still have a 0, and the image activator will have to fill it in. But if you're stepping through in the debugger and you followed your way through there, you would see all those addresses. But in the object, you're not going to see it. And so in the object, there's zeros here. If I dumped out the object and look for, show me all the pending relocations, the compiler has told the linker, this is what I need for all of these. And the same thing here for this call to this routine in the Pascal RTL. It's like, dear linker, I need call queue takes it how many bytes forward or how many bytes back that I need to call. We don't know where that's at. Certainly not within 2 to the 32 bytes with us. It's going to be somewhere else. So it's going to be, dear linker, generate me a trampoline routine near me that I can call to that will find the real thing by going through the GOT. And if I back up a minute, remember I had these linker generated things here, and that's that routine. So you see these zeros. If we also then in the exe file, so this is the exe file, and so same thing, I've dumped it out, and this is analyze image / segment equals code. We'll dump out the code, show you the instructions, a little different format, and here we can see where the linker has said, I am going from this PC at this distance will get to a slot. At this PC, this distance will get to a slot. And the analyze tool kind of told you it did the backwards arithmetic. This is the slot in the GOT that you're trying to access. Still don't know if you went to that address and looked there, it's still in the .exe file, still has a 0 into it. Somebody's going to fill that in at image activation time. But all these things are in here, including and you'll see a bug here. This is the code. Here are the 2 linker generated trampolines for the, I think the call will be enough. There's the calls here. So this call 24 bytes forward from wherever it's at gets me to this address and at this address. And so analyzed object has a bug. We're going to fix that. It started decoding this at offset 61 versus 60. Imagine that FF was in front of there. So there's actually 2 trampolines. Here's what a real trampoline looks like. It's a jump indirect through another offset to the GOT, and there's another address of the routine in that GOT, and we're going to jump through it because we don't know where paths dollar right string would be. All I know is I need to call it, and call doesn't take enough of a distance, so I have to call to another routine that does a 64-bit jump. All of this you should be really either impressed or depressed by.
I'll go with deep breath.
So I think we've got to get to the end of our time, right?
You have more trampolines than a health club.
Yeah, so there's a lot of the stuff in there. So if you dump through, you can see all of this stuff, and this all happens behind your back. The debugger knows about this stuff. You set a break on a routine, you'll never break it this thing. You have to go out of your way to actually break it. The debugger sniffs these things out. When you even step into, we jump over all this stuff. We're not going to make you jump through, watch any of this stuff, right? So the debugger knows about it. I don't know if SDA knows anything about it, but the debugger certainly does, right? And by the way, all these zeros is just an alignment at the end of this code. These got started on another, like an octa-word or a 32-byte boundary. These are zeros, and this is by default. 0 is the add B opcode, and so that's just the instruction decoder doing something stupid. I would like to actually notice a bunch of zeros in a row and format that as like .align 32 or something like that to make you realize what we're doing. We're just jumping to real
How about
line.
no ups?
Well, they actually are turned, but yeah, there's multiple sizes of no ops on x86.
I asked you to know that the single upgraded to more or less or the same relative amount of chipset as it would have on i64.
More slightly, but to be honest, the short section on Titanium still needed an address that has $right string. The short section there still. So if you look in the dynamic section, I'm not going to go. I have nothing for this. Analyze image segment equals dynamic. The image activator still fixes them all up. There might be a few more, but in general, the Titanium image activator was already busting its butt doing all this for that. We're probably done. I just wanted to mention quick things about stack walking. We have all these things. If you've used any of these create info contexts on the i64, they're exactly the same. We changed the name just to kind of make it trick because more than likely the invocation context block, the routines are the same, but what it's returning to is this big data structure, the ICB, invocation context block, and it's hardware dependent. It's full of registers. And the registers are different anywhere. You want to walk up the stack and look for what's the return address or that. We've changed the name just to make you come visit the code. Right? So do that. And if you've ever wanted to use that, going ICB gives you just addresses. You've ever wanted to know what does the address mean and how does the trace stack utility work? It reads the dwarf information, pick things out, but the traceback is callable. If you haven't noticed before, we did this years ago. Few people remember. You can write your own traceback utility if you want. So if you have a program, and let's say you have an exception handler, and you say, what happened here? And you want to, in a log file, write out, here's the call stack. And it's not just the raw addresses, and then you have to go find the listing file and the map file and your hex arithmetic calculator and a pencil and paper. We'll walk back up and format for you module routine through line 12, just like you would see in the debugger, a show calls, or just like you would see in traceback. So for people who haven't seen this, it was there on Alpha, it's there on Titanium, it's there on x86. I just want to throw that out as people to use that. There's an example in the code. It's not the easiest example in the world to follow, but it's actually, I think, written in C. Didn't like write it in Ada or PL1. Okay, so I think that's enough for us. I think that was it. Thanks. And